Okay, so let me introduce the next speaker then. His name is Hansu from NVIDIA, and he's going to talk about OVN-Northd incremental processing in C, the methodology, achievements, and challenges. Thank you. Take it away.
Hello, everyone. I'm Han from NVIDIA. My topic today is OVN-Northd incremental processing in C. Firstly, let's review the scale challenges of OVN control plane. There have been several bottlenecks in OVN control plane, including OVN controller, source-bound database, and OVN-Northd. And in the past few years, there has been a lot of improvements related to OVN controller and source-bound database. But for OVN-Northd, although it's also received a lot of improvements, but it's currently the biggest scale bottleneck of the OVN control plane, mostly because of its always recomputing everything for any input changes. And currently we're improving OVN-Northd by increment processing. Now let's look at some fundamentals of incremental processing with the analogy of materialized views in a relational database. So in a database, you can create views with some SQL queries, with operations like natural join against existing tables. A materialized view is something that pre-computes the result by executing a query beforehand and store the result physically, instead of executing a query on the fly. For this to work, it also needs to handle the changes in the source tables. A simple implementation is when any input changes, it just re-executes a query against all the existing data and recompute the result, which is obviously not efficient. A more efficient way is incrementally processing the changes. In this example, if there's a new record added in employee table, we'll need to probe the department table and properly generate a new record in the view. And if there's a change in the departments table, for example, the IT department changes name from IT to cloud, then we'll need to find out all the impacted records in the view and update them accordingly. This requires keeping the links between the input tables and the results, so that when anything changes, you can find out what's need to be updated. There are actually two approaches that can implement increment processing in OVN-Northd. One of them is DDlog, which is a domain language-based implementation, and once implemented, it will automatically process everything incrementally. But there are some problems, like it starts up much slower than the C implementation, and it might be harder to debug once everything, if there's anything goes wrong, because it's a separate implementation for the domain language itself, just like some database engine. So if anything goes wrong there, not everybody can easily debug it. Because of this and some other reasons, this approach is paused for at least more than a year. What's currently going on is the C implementation. We're trying to implement something with relatively small effort to achieve the best outcome. And with this goal in mind, we are not trying to incrementally processing everything, but only for the most frequent changes, the changes that is critical to the overall scalability. And in the C implementation, we have the capability to fall back to recompute when the change handling is too complex and not performance critical. The problem of C implementation is that it's not a language that can easily guarantee the correctness, but we have developed the increment processing engine when we were implementing increment processing for OVN controller. Although it's not perfect, but it proved to be quite helpful for the correctness and maintainability. So with the engine, you can define a directional acyclic graph, as what the picture is showing here. And there are important things to consider when implementing an increment processing engine node, or when you're doing a code review for such changes. The first thing is the date of the node, which is pretty similar to the materialized view in the previous example. And then the dependency. What are the inputs of this node, and what are the node that depends on this node? And then how is the data computed, which corresponds to the join operator of the previous database example. But here, of course, the operator can be as complex as any C function. And the most important thing, or most critical thing for the incremental processing is how the input changes are handled. And then what changes are tracked in this node. And finally, how are the changes handled by its children? And probably 1 or 2 years ago, the incremental processing engine has been adopted in OVN-Northd to achieve some initial state, so that if there's no change, then no compute. But if there's any change, then we just do the recompute. And this achieves some quiet state of OVN-Northd when there's changes not related to any flow-related processing, then OVN-Northd CPU is very quiet. For example, events such as OVSDB probe won't trigger recompute, and OVN-Northd CPU will be very quiet in that situation. But still, if there's any meaningful change happens in the data center, the OVN-Northd will be very busy. And after that, there are also some incremental processing engine node added for some no-high inputs, such as address set incremental processing, which is not directly related to logic flow computation. But in general, the initial state had all the northbound and southbound tables as inputs, and all the internal representation of the data as a one big engine node. And another big node is for the logic flow computing. So to implement more fine-grained incremental processing, the first thing to do was refactoring. And the purpose is to identify the dependencies more clearly for the logic flow generation and other computations. To make the dependency clear, we need to make sure the dependencies are traceable through function parameters. So we did a lot of work for the data structure reorganization and avoid implicit dependencies introduced by global variables, and also sanitizing function inputs, such as avoid passing wrapping structures, some data structure that wraps a lot of data, and you cannot easily tell if this function really needs that input or not. And also remove, by breaking the wrapping structures, we also could remove unnecessary inputs. And again, the goal is to make sure we can easily tell the dependencies just by the function prototypes. And after refactoring, we could draw this dependency graph of OVN-Northd at the time. I believe it looks very messy, and believe me, this is still incomplete, and there are other nodes that just can't manage to fit it in the same picture. So as we can see, it's not realistic to incrementally processing everything, because the dependency was just too complex. And our approach is to gradually implement it, and I'll call it incremental development. So the first thing is to identify the most frequent changes, that is the bottleneck of scalability. For example, the VIF logic switch port creation and binding related changes, which is directly related to the virtual machine or container creation, deletion, obviously as the most frequent events happening in any data center. And secondly, we use a top-down approach to analyze what are the dependencies that is related to these input changes. And then we can implement corresponding incremental processing engine nodes and change handlers to handle those changes incrementally. So how do we identify a VIF, not switch port related inputs? There are actually two parts. So the first thing is the northbound notch switch table. And the notch switch port table is actually referenced by the notch switch table. So we don't have a notch switch port as input. And the second part is the southbound port binding table, which is directly related to port binding when there's a update in the chassis column when the port is claimed on a chassis. So from graph, we can tell these are the nodes that's related to the two input nodes. But there are still too many. Actually, many of them are not directly related to VIF changes. For example, these notch router data passes or notch ports, although they have a dependency on the southbound port binding table, but that dependency is because of the notch router port related port bindings, not for the VIF related. So we're taking an approach when we implement change handlers, we only handle the specific type of changes that we're interested in for this specific VIF-related changes. If anything else is changed, we just fall back to recompute. With this approach, we can ignore most of the data and only focus on the parts we're interested in for this specific input, and make it incrementally processed end-to-end. And this picture is not reflecting the actual status of what's being implemented in the current implementation because of some challenges of actually breaking the engine node into smaller ones, which I will mention later. And this is how it looks like in the current implementation. Although we have logic separations of the data of logic switch data paths and logic switch ports, but they are still part of the bigger NOSD data engine node. With all these efforts and some other improvements, such as avoid recomputing when there are in-flight OVSDB transactions, and things like when we receive OVSDB update notifications from the OVN-Northd transaction itself, we achieved the status of zero recompute for some of the scenarios. In a scale test environment of simulated OVN Kubernetes topology of 500 nodes, each with 50 logic switch ports, the end-to-end VIF creation binding time is reduced more than 95%. It's more than 20 times faster. With the below constraints, so firstly, the logic switch ports are not part of any service backends. And also the logic switch port are not part of any port group that's attached to echoes. And the second constraint is actually partially removed by Dimitri's incremental processing implementation for port groups. And also from Newman, he implemented the node balancing incremental processing in the NOSD node, which has achieved more than 50% CPU savings, or it's more than 2 times faster in the OVN heater testing for the density-heavy scenario. And Newman is currently continue working on load balancer incremental processing for the logic flow node, which would achieve end-to-end incremental processing for load balancer. And I'll go through some so-called disciplines for the incremental processing, which I think is important for the correctness and maintainability. The input node data access should be read-only, and we should avoid direct pointer references between nodes. Otherwise, we would introduce implicit dependency. And we should also avoid silently ignoring input changes in change handler. And we should strictly follow the compute logic when implementing change handlers. If it's too complex, or when we are not sure about the correctness, we should fall back to recompute. For the test cases, we should compare the incremental processing result with recompute result. And even though it's not 100% guaranteed to be correct, because we might miss some increment processing test coverage. But whenever we have the coverage, we need to make sure it's correct by comparing with the recompute result. If there are any exceptions to the rules above for any good reason, we should carefully document it so that people reading the code or making more changes can understand the reason behind. And let's look more about references between nodes. In this example, A depends on B and C depends on A. So when A is computed, in this example, it stores the pointer of an object of B directly in A's data. But because A is input of C, it becomes possible that we directly use B's data through the pointer that stored in object A. This ends up with implicit dependency. The consequence is there's no change handler implemented in C for the input B because it's not required from increment process engine. So when B's data changes, we should actually evaluate if there's any update needed for C's data because of this dependency. But unfortunately, this is not represented in the increment processing engine, so it's not going to happen. And the correct implementation should be storing a key of B's object instead of storing the pointer directly. And in the implementation of C, it should actually look up B's object from B's data according to the key instead directly using the B's pointer. And this would require dependency explicitly represented from the engine node, from the increment processing engine. So any change of B should trigger either a recompute in C or a change handler execution for increment processing. Another issue of the references between nodes is kind of circular dependency. And this is one of the reasons why we didn't split notch switch ports from the Northd data node. In this example, the notch switch port is connected to a notch router, so it actually has a peer port as a notch router port. And the notch router port has a peer also to this same notch switch port. So from the data structure, they actually depends on each other. So if we really want to break this into separate nodes, we need to break this circular dependency. And the natural approach is to create a third node that maintains the mapping between these two nodes. And another challenge for the increment processing is when there are multiple inputs and we want to implement increment processing for more than one input. In this example, A is primary input of C, and B and other inputs are secondary inputs. So in the recompute function of C, we usually have this logic that for each object in A, we have a main function that can build the object of C. So A is the main input, and B and other inputs are kind of associated data that can be queried when we generate object of C. In this case, when there's any new object added in A, we can just call the same function for those new objects. However, if we want to implement increment processing for the secondary input, in this case B, it becomes more complex. Let's say we added a new object in B, then how to implement the change handler in C. If we want to reuse the same function that generates the C for each object A, then we need to figure out what are the object A's impacted by this object B change. It requires us to maintain a relationship between A and B so that we can tell what A is impacted when there's change in B. This is actually how we implement the OVN controller, where the primary input is the logic flow, and the logic flow can reference some other objects such as address set, port group, etc. And those are the secondary inputs. And there are always direct relationship or references between the logic flow and the resources it's used. However, this is not always the case in NORTH-D. A and B and other inputs can be totally independent, and it might be very complex or inefficient to create links between them. Or we should implement some different functions just to handle B's change. And we cannot reuse the primary function that is implemented for the recompute. And we all need to do this for different inputs if we want to process them incrementally. And finally, I'll give an example of an incomplete change handling implementation which ended up with a bug. When the first or last logic switch port is added or deleted from logic switch, there are flows related to router IPs that need to be updated. But the logic switch port being added or deleted themselves is not a router port and doesn't directly related to any router IPs. In the initial implementation of the change handler, when the logic switch port is created or deleted, we simply call the related functions to generate or delete relevant flows. But in the implementation of recompute function of the logic flow node, there are actually logic that depends on this condition. It checks if the number of router ports is equal to the number of switch ports in the logic switch. So when the first or last logic switch port is added or deleted, this condition actually would change. And when this condition changes, the router IP related flow will need to be updated, which is actually a result of processing router ports on this logic switch, which are different from the port that's being added or deleted. And the fix is quite simple once it's identified, but there are lessons learned. The ad hoc implementation is actually quite error prone, and it's never enough for more testing and code review. Okay, this is the end of my presentation. Thanks for watching.
All right, thank you, Han. Let's see if there are some questions there. 1 second, let me pop up. Yep, I see there's already 2 questions. So the first one is from Newman. If we have to keep adding IP for many northbound changes scenarios in order to address skill requirements, do you think we should stop adding IP and re-evaluate the different implementations of the OVN-Northd?
I think as it's getting more and more complex, it's not realistic to incrementally processing everything, as I mentioned in the presentation. So it really depends on our scale requirements. If we believe there are many more changes still required to be incrementally processed for us for OVN to scale in a reasonable production environment, I think we need to consider a different approach. For example, the DDlog shall we retake it, but seems the maintainability is the problem of DDlog. Or should we explore a different language, because in the C processing, it's really, really difficult to make it correct with all those changes.
Okay, thank you for answering that question. We have another question from Dumitru, and he suggests, would reducing the supported feature set, e.g. a simpler logical router with less features, make it easier to implement a simpler or cleaner incremental processing? And is that a trade-off that we're willing to accept?
Yeah, I think so. Basically reducing the support feature, but it really depends, right? What kind of feature can be actually sacrificed? But in general, yes, I agree with this principle. We need to consider basically trade-off between the incremental processing complexity and the feature really needed for the production environments.
All right, thank you. I'm just going to quickly check if there's more questions. I don't think there are any. No, I think that's it for now. So thanks again, Han, for your presentation and all the details you put in the slide.